up, guys? Welcome back to another Algebra 2 instruction lesson here with Mr. Gaines as we have been exploring the exponential function. Today we are going to kind of elaborate on what we did with the last video and look at a specific special base which is known as Euler's number. So Euler's number is actually the limit for an expression. So this expression is 1 plus 1 over x to the x power. And what we're looking for is the value of that expression as x approaches infinity. So let me give you a visual on that. So this is the graph for 1 plus 1 over x to the x power. A very interesting graph as we take a look at it. But what we're looking for is a limit on we're looking for the y value as we go to the right. So you can see that it's 2 point something, and this decimal is steadily increasing. And let's really get really far out to the right here. You can see that it's 2.7 something, but it's still going up the further that I go to the right. And let's get even further out here to the right. And there it's 2.718, and it's actually continuing to increase as we go further and further. If we could have more decimals, you could see that. But this is going to be an irrational number, a decimal that runs forever. It never finishes, kind of like pi. But our approximation for it is 2.718. So Euler's number is going to be very beneficial when we deal with logarithms that we'll approach later in this unit. But for right now, let's work on evaluating Euler's number. So we can evaluate Euler's number through the calculator. I'm not going to have you guys do that by hand. With an irrational number, it's extremely difficult to do. So what we're going to do is use the calculator to evaluate Euler's number. And that value is actually located on the calculator. It's a button. So if you look at the ln key here, right next to the 4, there's this ln, or what's called the natural log key. And to the top left, we see e to the x power. So we can use that to evaluate any power of e. So if I want to evaluate f of 0, this would be e to the 0 power. Everybody should be able to do this. Any expression to the 0 power is 1. So e to the 0 power is just 1. Everybody should know that. But then we go a little bit further. E to the first power. So we can evaluate e to the first power in the calculator. And it's 2.78. You can see that decimal 71828 and so on and so forth. You can see that decimal goes on and on and on. And so we'll just go ahead and round it to two decimals here. So this is going to be approximately, let's use that approximate symbol, 7.2. And then as we increase the value for x, we're going to increase the rounded value for Euler's number. So again, we have to hit that second key and then the natural log, and then we can use that to approximate the value. So this would be about 7.39. And now we are taking a look at, in D, an exponent that is rational. And so this would essentially be the root of e, square root of e, which is going to reduce its value, and it would be approximately 1.65. So we can use the calculator here. We're not going to evaluate these by hand, not for our purposes in Algebra 2. We can use the calculator to evaluate those numbers. Now, what I want to do also is take a look at graphing Euler's number. And we're going to continue this with some work with our transformations that we saw previously. So here in problem 6a, we want to graph the functions. What they give us is the base b is going to be Euler's number here. So that's that irrational expression, approximately 2.72 or 2.718. Now, we have some shifts here. We have a horizontal shift of to the right 1. And we have a vertical shift. This vertical shift is going to go down 8. So I'm going to go ahead and shift this down 8. And that's going to move my horizontal asymptote down 8. and then I'm going to shift the origination point. Remember, all exponential functions start with a point 0, 1 before transformations. That is going to be shifted to the right 1 with the horizontal shift, and then down 8. So we're going to have this point at 1, 7. And now, because Euler's number is an irrational base, I'm just going to go ahead and use the calculator to help me plot points that are going to exist on this function. And what we know or should know here is that Euler's number is above 1. So this is going to be exponential growth. And so we can see that in our graphing calculator here. So it's going to the left, it's going to approach the asymptote. So to the left of this origination point, I'm just going to draw that going down to the asymptote. To the right, I'm going to go ahead and plot some points. So here's my origination point that's at 1, 7. And then 1, negative 7. And then at 2, negative 5.2. So this is going to be between negative 5 and negative 6. Just pretty close to negative 5. Then 3 is at negative 0.61. So this is going to be almost in the middle of 0 and negative 1. Then 4 is going to be at 12.08. So this would come off of our graph, but I'll go ahead and estimate that value up here. So as we approach this curve going to the left, it's going to get closer and closer to this asymptote. So I'm just going to draw that in there, not crossing the asymptote, but getting close to it. And then as we go to the right, I'm going to draw my curve through my points. Sorry, I was on the wrong line up here. I'm going to draw my curve through my points to show that exponential growth. And there we have a graph of f of x. Now g of x is going to be a little bit different. So let's take a look at what we have here. We have a vertical shift. We have, in b, we have another base that's going to be the Euler's number. Here we have a vertical dilation. So notice this is the first time we've seen one of these in the notes. But notice that the exponent x is attached to E, Euler's number, and 3 is being multiplied to that. So we have a vertical dilation. This negative out here is a vertical reflection. So we have a couple of different transformations going on here that we've seen so far. Let's go ahead and start with the vertical shift moving the vertical asymptote. So the vertical shift is going to move the vertical asymptote up 4. Now my point 0, 1 is going to be affected by each of those transformations. So again, they all exponentials start with a point 0, 1. So if it was first, let's say it's reflected vertically. So before any shifts, it's reflected across the x-axis. A vertical reflection reflects across the x-axis. So it's going to come down to 0, negative 1. Then from there, we're going to apply the vertical shift. Sorry, from there, we're going to apply the vertical stretch. So we reflected it down to 0, 1. Now we're going to stretch it. So we're going to triple the distance from the x-axis. So 1 times 3 would be 3. And then we're going to shift it up 4. 1, 2, 3, 4. So after all of those transformations, the point that started at 0, 1 is going to actually end up back at 0, 1. But notice that for the first time that we have seen so far in our graphing process on the notes, that the origination point is below the horizontal asymptote because we have that vertical reflection. Now let's go ahead and use the graphing calculator to help us get our points. We know that this is going to be an exponential growth. So before being reflected, it would have looked like that. So the reflection is going to look something like this. Those are not exact points, but you get the idea of the curve. So it's going to approach the asymptote going to the left. It's actually going to go down to the right instead of up like we normally see with an exponential growth because it has been reflected. So let me take a look at the table here. Sorry, there's the graph. Let me take a look at the table so I can get some points. So I'm going to plot a point to the left of my origination point here. I'm going to have negative 1, 2.8. So 2.8 is almost to 3, but not quite. and I'm going to have negative 3 at, or sorry, negative 2, 3.5. So that's almost 3.6. That's almost directly in between negative 3, or positive 3 and positive 4. I'm going to have a negative 3, 3.8. So that's getting me really close to the asymptote. So I'll just leave that point right there. I want to go to the right of my origination point here as well. So that point was at 0, 1. Now I have 1, negative 4.2 approximately. So very close to negative 4, between negative 4 and negative 5. And then I'd have 2, negative 18. So that would be way off of the graph. So I'm not going to graph that one. And from here, I can go ahead and draw in my curve. So there we can see that we have the same concepts as before with these exponential functions, with the transformations. They're the same concepts, and the horizontal asymptote. All of that is still carried over from what we saw previously with exponential functions. We just see a different base. Now, I did not put in the domains and ranges initially when going through, but you guys should be able to get those. The domain for both of these is going to be all real numbers. So both of these functions are going to have a graph that goes to the right forever and goes to the left forever. The domain of, or sorry, the range of a, f of x, this function is going up forever, so it's going to be above the vertical asymptote, or sorry, horizontal asymptote, which is y equals negative 8, so it's going to be greater than negative 8. The range for f of x in b, it's below the horizontal asymptote, which is y equals 4. And again, it's never going to intercept that, so it's going to be less than 4. So here we have just some examples of graphing using Euler's number, which is a different base, a base that is an irrational number. But we can still use a combination of transformations and the calculator to help us graph. This looks like a good place to stop for this section. As always, thank you guys for tuning in, and I'll see you soon.